Hello, thank you everyone for joining our webinar. This month, I am really delighted to have Dr. Robert Borden. I've worked with Bob and Ann for many years, and not only does EOS have exceptional products, but you'll find that they have vast experience and expertise in so many different areas. So it's really an honor to have Dr. Borden speaking for us today. And the size of the audience that we have on the webinar definitely attests to his vast knowledge. So I'm glad that we can have you here today, Dr. Borden, to talk to us. Although you really need no introduction, I'm going to give a short summary. Dr. Borden serves as the principal engineer at EOS Remediation, and he's professor emeritus at North Carolina State University. Bob has over 30 years of experience in the development and implementation of technologies for in situ remediation of contaminated soil and groundwater. Specifically, Bob has developed technologies to stimulate in situ biodegradation of petroleum hydrocarbons, chlorinated solvents, explosives, propellants, and 1,4-dioxane. Results of his work are published in numerous journal articles, reports. He's made design tools and protocols, computer models, and he developed a really interesting site that you should all check out called EnviroWiki. So during the talk today, Dr. Borden is going to be talking to us and focusing on DCE stalls. And he's going to do this webinar a little different than what you guys have seen with us in the past. Go ahead and enter your questions in as you have them during the first part. We're going to kind of stop in the middle of his intro, and then after that we'll go through the questions that you guys have, and then he'll finish out talking more about DCE stalls after he answers your question. So we're going to kind of do a two-part question, one in the middle of the presentation and then again at the end. So go ahead and enter your questions into the GoToWebinar software as you have them, and that way we can get to them quickly. So he's going to be talking today about the causes of DCE stalls and then how we cure it. So as many of you know, this webinar is going to be recorded. It'll be on the resource section of the Microbial Insights website. You don't have to email anyone. You're automatically going to get a link for everyone who registered as soon as it's available. So again, we're going to have a two-part question and answer period, one in the middle of the presentation and one at the end. So go ahead, type your questions into the GoToWebinar software, and we'll get to them as quickly as possible. If you have other questions that come up after, you can always email Dr. Borden, or you can email us, info@microbe.com. We'll get with him, get the answers, and get that out to you. So without anything further, I'm going to go ahead and turn it over to you, Dr. Borden.
Thank you, Dora. Well, I was gonna give you my description, but Dora just did. But anyway, so I'm Bob Borden, and well, let me just move along to the sort of overview. So first of all, sort of a disclaimer or explanation. I'm not gonna be presenting sort of new research here. It might be new to some of you, but I think most of the stuff I'm going to be presenting has been put together in different places, and a lot of it's just basic microbiology. But I do feel like that, well, hopefully I'm gonna get to point out some new things to you. Most of the examples I'm going to be talking about are related to emulsified vegetable oil, but we have done some studies and shown that really the results with soluble substrates like lactate and molasses really are not very different, and I'll talk about that. I'm going to talk about 3 indicator parameters, some of ethenes, some of organic chlorine and chlorine number, that I personally find very informative and useful to look at. I'm going to share with you some, I guess it's called data mining results, but results from some large-scale monitoring projects, as well as, and then we'll sort of dig into the microbiology a little bit more about what the factors are that appear to limit DCE conversion of biochloride and ethene. And then finally, if I have time, this will be the second half of the presentation. I'll dig into the details about how to actually improve substrate distribution and how to adjust pH to where you need it. Okay, so indicator parameters I mentioned, you've all seen that diagram at the top. PCE goes to TCE, goes to DCE, goes to vinyl chloride and ethene. When you look at this data, it tends to at least make my eyes sort of go cross where, you know, PCE or TC goes down, but DC goes up, vinyl chloride goes up and down. And it's really hard to sort of figure out what's going on sometimes as these parameters bounce around. So I use these different indicators. What we'll do is we'll basically take the measured concentration in a well of each of the compounds, divide it by the molecular weight, and that way you convert the concentration from milligrams or micrograms per liter to moles or micromoles per liter. Sum of organic chlorine is essentially the number of moles of chlorine associated with ethynes. So since PCE has 4 chlorines on it, well, you take the chlorine, the molar PCE concentration and multiply 4, the molar TCE concentration by 3, and the molar DCE concentration by 2. Sum those up, and that would be the sum of organic chlorine. And chlorine number is just the sum of organic chlorine divided by the total ethynes. And I'll show you in this slide just sort of how you use this information. What I'm showing you is data from one monitoring well. And, you know, this well was first injected in 2006. They went back and, well, not this well, but this area near this well was re-injected with EOS Pro and buffer in 2012. If you look at the graph at the top, you see ethynes on the axis on a log scale, and you see that the initial let's see, TCE concentration was, well, I don't know, anywhere from 5,000 to 10,000 micrograms per liter. And it took a couple years, but within 3 years, let me go back. The the TCE concentration has declined by 1, 2, 3, almost 4 orders of magnitude. So 99.99% reduction. Anybody I know would think, wow, that's pretty good. But you also looks like, you know, we have sort of the classic DCE stall there, where TC went down, but I've got really high concentrations of DCE, and the DCE doesn't seem to be going down much, or at least right here till the end. So, you know, that's sort of classic DC stall. Okay, obvious question is, okay, well, we don't have bugs, you know, maybe we should buy augment. Well, the problem is they buy augmented early on. And the other problem is you look at this black line, we're making at least 100, maybe 200, 300, 400 micrograms per liter of ethene. We're making a boatload of ethene. So this isn't exactly stall, but, well, it certainly doesn't look like we're making a lot of progress there. So, you know, to a certain extent, it's sort of hard to dig out, well, is this doing really good or is this not so good? And so that's kind of why I like to use these indicator parameters. Down below, you see the red is sum of ethynes. It, you know, goes down a little bit, but basically from 2009 to maybe about 2014, there's no change in sum of ethynes at all. It looks like there's a little bit of decline in sum of organic chlorine. Now, if you take the ratio of that below, you see that where initially chlorine number here, which is the sum of chlorine, organic chlorine divided by sum of ethynes, here it's about 3. So basically what that's saying is it's virtually all TCE. And then by 2009, it drops down to about 1. Basically what that says is you've got about, you know, you've got a roughly even ratio of DCE to TCE to vinyl chloride to ethene. So you all average that out. It's kind of an average of one, which be sort of an average of vinyl chloride. And it really kind of stays constant there for several years and then kind of slowly declines. And it's not here till what, I guess about 2013 sometime that we really see the chlorine number drop off. So, you know, this to me, you know, I'm going to say, since we're sort of hanging out here at this level, I don't know if that's a DCE stall or a vinyl chloride stall, but certainly, you know, it's not progressing quite the way we want it to. And I think that's what we see much more often. Not that there's no ethene production and there are no bacteria, just that, well, we did such a great job of degrading TCE, and the TCE degradation rate is greater than the DCE removal rate. So we see like this accumulation, and it often hangs out here for a long time, or at least a lot longer than we're hoping. So when I talk about DCE stall, it's not that we're not getting any ethene production or we don't have the helicocordes. We're just not getting as rapid a removal of the DCE as maybe we would like. Okay. We worked on a project for a number of years for CERTA. And what we did is the objective of this project was to go out and look at secondary water quality indicator parameters from a whole series of enhanced reductive dechlorination projects to see if those secondary water quality impacts were significant. And I'm not really going to focus on that in this presentation, but it's sort of part of that process. We're compiling all this data on methane and sulfate and TOC. Well, we decided we'd also look at effects on dechlorination. And what I'm showing you here is a graph of a single well, a series of graphs. And what you see here is when plotted on a log scale, PCE went down, you know, really pretty rapidly and pretty steadily. TC went down, while DC went up and then started to go down. And vinyl chloride stayed constant and then went up. And so it's, well, PC and TC are going down and DC is bouncing around. To me, this is a hard data set to look at because you're so, well, is it good or bad or both? And so that's why I feel like looking at some of organic chlorine sort of summarizes this and simplifies a little bit. So if you take all this data, you can convert it to one graph. Here are the results, and here's some of organic chlorine versus time. And you see that, well, initially there's not much change. We have a degradation period. And then we can see actually after a certain decay period, sort of this stall period. And to me, this data is a whole lot easier to sort of digest. And we've got these statistics for, well, as I indicated here, 47 ERD sites. 14 of them were soluble substrate sites, 21 were EVO, and then there's a couple sites where they used a mulch biobarrier, and then 10 other sites that were some combination of soluble substrates in EVO. About half barriers, half source areas, and anywhere from a half a year up to 11 years of monitoring data. So we had a lot of data to look at. And what we tried to do is use this procedure, get the individual rates, and try to figure out, well, you know, what was sort of typical behavior at ERD projects. And here's the results. So we've got about 100, I think it was about 184 wells we looked at. And when you looked at, and what we could break them down into was light blue is the contaminant is decreasing, white is stable, or red is increasing. And then you've got these intermediates. And you can see here, in most of the sites, PCE and TCE were going down. In a smaller percentage, these compounds were going up, or they just weren't changing. versus when you go over here to DCE and vinyl chloride, the fraction that are going down is much smaller, and the number of sites where it's going up is significantly higher. We all know that degrading DCE and vinyl chloride is harder than maybe these other parent compounds. This is no big surprise. But what I wanted to present here is that, well, of a pretty good database of sites, no decrease in the number of sites where vinyl chloride is increasing is comparable to the number of sites where it's decreasing. And so, we've got a fair number of sites where, again, I don't think this is necessarily a stall. That's why I put it in quotes. But it's certainly vinyl chloride and DCE are not degrading maybe as rapidly as we would hope. We were able to take it of those sites where compounds were decreasing, we extracted out the actual degradation rates. And again, you see here that PCE and TCE and tend to degrade more rapidly, no big surprise. DCE and vinyl chloride degrade more slowly. Total organic chlorine degrades actually even slightly slower or maybe the same as vinyl chloride. And in a way, I feel like that degradation rate for some of organic chlorine is really probably more representative of the overall progress. If we do really great removal of TCE, but then it solves the DCE, well, we still have compounds in the ground. We still have contaminated groundwater. Okay. One other thing I wanted to share with you from this database survey was data on organic carbon concentrations. What we're showing here is this is a cumulative frequency graph. So I've got on the bottom axis maximum observed TOC concentration. We didn't do average, we didn't do individual measurements because in a lot of cases, people, particularly with soluble substrates, you'd go out, you'd inject it in the ground, you'd see a big spike in TC and then it would go down. And sometimes that average is, it really depends on when you monitor, did you hit the right thing, date. So we thought the best thing to do was look at, well, what's the maximum TOC that was ever measured in a well? And so, for example, the solid circles, that's the background levels of TCE. And what it says here is that 50% of the wells had a maximum TOC less than what? Maybe that's 3 milligrams per liter. Maybe 75 or less than 10 milligrams per liter. So this and what I guess the maximum value measured was about 200 milligrams per liter in the background wells. So these are low levels. Now in the injection area, the median TOC concept, this is kind of strange. These are all maximum measurements. So in half the wells, the maximum observed TOC was over 250 milligrams per liter. In half the wells, the maximum TOC was less than 250 milligrams per liter. If you go if you go into monitor wells anywhere between 0 and 10 meters down gradient, the maximum TOC ever observed, that's about 50 or 60 milligrams per liter, 57 milligrams per liter. So what you see here is injection wells concentrations are pretty high, or in the injection zone, concentrations are pretty high. None of these are actually injection wells. Just, well, an average of 5 meters down gradient, 15 feet, it's decreased a lot. And there's quite a few wells where, the maximum TOC is 10 milligrams per liter. If you go in the range of 10 to 25 meters down gradient, much, much lower, now only a few milligrams per liter TOC. So what we see here is that dissolved TOC that people measure doesn't migrate. It, or it only migrates a quite a short distance. I don't have the data to show you here, but we actually partitioned this data and we looked at sites where they used emulsified vegetable oil versus soluble substrate. There was basically no difference. Whether you used EVO or used soluble substrate, TOC did not migrate downgrade in any significant distance at all. So I know a lot of people talk about that, but at least the data we have says that, you're really getting good TUC numbers right in the vicinity of the injection zone, and hoping that it's going to migrate a significance down gradient is probably not going to happen. I know some people do that, and there's certainly, I want to take an exception here. There's people that have sites with groundwater velocities of 1,000 feet per year. Sure, it could certainly migrate down there, but I think in a lot of sites, TUC does not migrate significant distances. Okay. Now let's go back. Hopefully I convinced you that we often see quite a bit more rapid PC and TC removal than DCE and vinyl chloride. Well, why? Okay, the obvious answer is the microbiology. There's a significant number of different organisms that can convert PCE to TCE to DCE. They grow, in general, their growth kinetics are fairly fast. They grow rapidly and they reproduce. I believe some other very important characteristics are that these organisms can use both hydrogen. Well, I don't want to say all the organisms, but there are some organisms that can use both hydrogen and acetate. Some of the research from Frank Loeffler's lab has shown that a number of these organisms can fix nitrogen out of the air. So you don't have to supply them with ammonia nitrogen. They can actually convert into to ammonia and use that in a metabolism. So that's a factor that doesn't limit. Many of these organisms can produce B12, so they won't be limited by that. And as I'll show you a little bit later, they tend to be less sensitive to low pH. I'll show you some graphs where people see actually really quite good PCE and TCE degradation down to pH 5.5. The counter side, the Helicoides McCarty, I know there's one other organism that people are talking about might be able to degrade vinyl chloride, but for now, let's just focus on the Helicoides. Number one, it grows slowly. Another big deal is it cannot use hydrogen as an electron donor. You have to supply hydrogen. No hydrogen, no degradation of vinyl chloride. It requires an external source of ammonia. It requires an external source of B12, and it appears to be a lot more sensitive to pH. Now I'm saying here pH greater than 6.3. I'm going to say that for good degradation of vinyl chloride. There's some cultures that people are working on that can now degrade vinyl chloride down to maybe 5.8, 5.9, but even then at those rates, at those pH levels, the rates are significantly reduced. So we have two different groups of organisms. The Helicoides not only normally grows more slowly under optimum conditions, but it's got a lot more specialized nutritional requirements. And if you don't supply it with hydrogen, you don't supply it with ammonia, you don't supply it with B12, and you don't keep a neutral pH, it's going to do very poorly. Okay, now I'm going to take a step back and I'm going to talk a little bit about, okay, where does the acetate and the hydrogen come from? And I'm going to talk primarily about soybean oil fermentation. Soybean oil, other vegetable oils, they're called triglycerides. And what it is, there's a glycerol core here, that's those red dots in the middle that form a glycerol molecule. And esterified on the end of the glycerol is 3 long chain fatty acids. Typically, natural fats have about 18 carbon atoms in them. So what first happens is when you add these materials to the subsurface, bacteria will break down, begin to break down the soybean oil. They'll hydrolyze the linkage between the glycerol and the long chain fatty acid, and they release that long chain fatty acid to solution. And they also release the glycerol. Glycerol is very soluble, very easy to degrade. It's, you know, it's equivalent. Sorry, my speakerphone is speaking. Okay, sorry, I got confused here. Glycerol, very soluble, very easy to degrade. It's like lactate or molasses. It'll either degrade or will float down gradient and disappear. Now you've got the long chain fatty acids. The organisms we care about cannot use directly long chain fatty acids as carbon source. They can't dechlorinate the compounds. But there are fermenters in the subsurface that do a process called beta oxidation. And what that means is they'll take one of these long chain fatty acids. I'm going to assume it's linoleic acid, although there's a couple of different versions, but they've got 18 carbons, they've got a bunch of hydrogen and 2 oxygen. Well, what organisms can do is they can take a C18 fatty acid, linoleic acid, they can add water to it, and in the process produce a C16 and release 1 acetic acid molecule and 1 hydrogen molecule. Then they can take that C16, again add water to it, now they produce a C14, an acetate and hydrogen. C14 goes to C12, and so on. So what these bacteria do is they sort of progressively whittle away the long chain fatty acid, cleaving off an acetate and 1 or 2 hydrogens. And so the net result is, once it gets down to the end here, is the long chain fatty acid produces a number of moles of acetate. In here, 9 moles of acetate and 14 moles of hydrogen. If it's a fully saturated fat, you'll get more hydrogen. Unsaturated, you know, everybody knows soybean oil is good for you. It's high in unsaturated fats, so it produces a little less hydrogen and more acetate. But anyway, or not more acetate, but so that's this sort of the net reaction there. So we're going to produce, by this process, acetate and hydrogen. Okay, why is good oil distribution critical? Well, that first step, when we release linoleic acid, if you're in an aquifer that has dissolved calcium, Ca2+, or magnesium 2+, well, long chain fatty acid, linoleic acid, well, that's a fancy scientific word for ivory soap. Ivory soap is actually linoleic acid plus sodium hydroxide, and it precipitates out its hard white bar soap. If that hard white bar soap is in low hardness water, it's soluble. But if there's a bunch of calcium or magnesium floating around, that linoleic acid will precipitate out as soap scum. Soap scum's got a very, very low aqueous solubility. So that long-chain fatty acid is, for all intents and purposes, not bioavailable once it's precipitated. And, I'm focusing here on calcium and magnesium, but you can also make soap scum from dissolved iron or dissolved manganese. So once we precipitate it out, it's got a very, very low bioavailability and is not really going to drive reductive decoordination. Now it's an equilibrium reaction, so there's always a little bit dissolved, and that small fraction that's dissolved will slowly ferment and it will release hydrogen and acetate. But since it's immobile, this linoleic acid or this soap scum we precipitated that really right around the oil injection zone. It's not going to migrate down gradient. And so what's going to happen in that oil injection zone, it's going to slowly biodegrade. That's probably why when we inject soybean oil, it lasts so long, because it's not bioavailable. But we inject soybean oil, these dissolved soap scum, the little low solubility soap scum, produces acetate and hydrogen. The acetate can simulate PC to TC and TC degradation. Turns out the energy yield from gross on acetate is a little bit lower. And so since it's not as good a substrate, it tends to migrate farther down gradient. And I'm going to show you some data where you actually do get a little bit of acetate migrating down gradient. In contrast, hydrogen is a great electron donor. It'll rapidly reduce the DCE in vinyl chloride diethene, but it will also rapidly reduce iron and sulfate. And if there's no chlorinated solvents around, it'll be reduced to methane. It'll reduce carbon dioxide to methane. So the net result is hydrogen is such a great electron donor, it doesn't really migrate down gradient any distance. It's only present where you produce it. Well, as I said before, hydrogen can be produced from long-chain fatty acid fermentation. Probably not a lot there because it's so insoluble, but things like degradation products of long-chain acids, propionate, butyrate, valerate, pentanoic, hexanoic acids, they all ferment, releasing more acetate and more hydrogen. Now, in theory, you can actually sort of drive the reaction backwards and produce hydrogen from acetate. In reality, that really does not happen. You have to have very, very strongly reducing conditions, and it's not going to happen. So the only place you're going to get PCE, DCE, and vinyl chloride degradation is where you have some of these compounds. Having just acetate won't do it. You need propionate, you need butyrate, valerate, things with more than 2 carbons. Okay, so let me show you some data. This is a site where we injected EOS Pro, and actually, in most cases, we don't have the data, but we actually monitored VFA concentrations in the injection well. Not surprisingly, injection well had great TOC numbers. We actually monitored TCE degradation actually in the injection well, got complete conversion of TC to ethane, like 99% conversion to ethane. It was perfect. Really high dolichoides numbers, great. Just 10 feet down gradient, we did get some organic carbon. The injection of EOS was, I don't know, it was late August. And 3 months later, we had a spike in TOC, 10 feet down gradient. 3 months later, it had dropped dramatically. And 9 months after the injection, well, we're down to about 10 milligrams per liter total fatty acids. But the key thing I want you to see about here is in the upgradient well, the injection well, yeah, we produced a decent amount of acetic acid, but we also had quite a bit of propionic acid. We had butyric acid and some other longer chain fatty acids. So we had a good, we probably had, let's see, 500 milligrams per liter of acetate, but then almost another 500 of these longer chain fatty acids that can be fermented and will produce hydrogen. So in this area here, we can produce a lot of hydrogen, get good, complete conversion to ethene. Here, yeah, we've got a little bit. Number one, look, versus here, this is 1,200 milligrams per liter. Here it's 120. So the maximum TOC is an order of magnitude lower, just 10 feet down gradient. And of that TOC, over 90% at best is acetate. Here we have virtually no of the higher long chain fatty acids. So 6 months after injection, there's essentially no long chain fatty acids at 10 feet down gradient, which means you can still degrade TCE and DCE here, but you're not going to get any further degradation of vinyl chloride at this point. Okay, other big factor I want to talk about is pH. And I know if you've seen, I beat on this a lot, but I think it's really critical. Here's some data from culture they identified from the Savannah River site. What you see here is at different pHs, they ran incubations and they measured TCE removal. The great removal at pH 7, slightly slower removal at pH 6.5 and 6, but even at 5.5, we're getting, essentially 100% removal at 20 days. So, rates may be a little bit lower than 5.5 at 6, but really not bad at all. It's not until here you get down to pH 5.5. I know you can't see those dots here, but, well, I'm sorry, that is pH 5.5. So even at 5.5, we're getting good removal. You look at vinyl chloride by contrast, good removal at pH 7, 6.5, a little bit of a lag, but still ends up having very good removal. At pH 6, strong inhibition. Yeah, you eventually get some. pH 5.5, zero degradation. So, if you're hanging out at maybe pH 5.8 and you've got limited hydrogen, well, what's going to happen? The bugs are going to do a very good job converting TCE to DCE. They're not going to do nearly as good a job converting vinyl chloride to ethene. Okay, so end conclusions. This is a project we did. We went back and looked at several sites where had previously been treated with EVO, and things were degrading, but they weren't quite going as fast as we hoped. And what we saw was that it was just simply that PCE and TCE were very rapidly converted to DCE. DCE and vinyl chloride I don't want to say all the cases, but a large percentage of cases, we were making ethene. We were producing ethene, and we had the helicoides. The problem is the conversion of DCE to vinyl chloride to ethene was slower than the conversion of TCE. So in the end, conversion of vinyl chloride to ethene was the rate limiting step in the cleanup process. That's controlled the time to clean up that. And as long as there was still a bunch of DCE and a bunch of vinyl chloride, you're going to have to go out, you're going to have to re-inject, you're going to have to spend money. and you didn't have a clean site. Our conclusion from the data was that in many, many cases, it was in less than ideal distribution of organic carbon. Yeah, we spread the oil out a little bit, but there were significant zones where there was chlorinated solvent, but not actually oil. So while maybe acetate was getting that location, hydrogen was not. And so we couldn't degrade it. At a number of these sites, we had low pH. We did not look at B12 or ammonia nitrogen limitations. It's certainly possible, but that's not something I can address. So I'm going to just have to leave that as a question mark. I felt like at the end of this project, we were confident, we could see at virtually every site, every well where we weren't getting the removal we hoped for, we knew what. And so I guess I'd like to stop right now and take some questions.
All right, thank you. Very good presentation so far. Okay, so we have quite a few questions. To what degree does the persistent vinyl chloride that we're seeing reflect back diffusion of TCE with rapid conversion to vinyl chloride? If vinyl chloride is also being converted to high levels of ethene, then it looks like good effective biodegradation. So do you think the VC comes from back diffusion and reduction of TCE, I guess is the main question?
I certainly think something like back diffusion was a contributor at some locations. I'm not saying it was necessary, but clearly TCE was getting reduced to DCE. Did that occur down gradient? I don't know the exact location where that, but certainly yes, we were at a location where there was enough reducing power in the acetate to convert the TCE to DCE, quite possibly down gradient. But at that point, there was no hydrogen, and so it didn't go any further. So I think I'm agreeing with your statement in general, but exactly the specifics of was it back diffusion? And I'll show you some other locations where they're just places where, we didn't treat the whole area and there were little holes in our treatment. But certainly that, yes, I agree with the general thought.
Okay, great. In the beginning of your presentation, you showed a column chart and it showed percentages of increase, decrease, and no change for each parameter of the wells. And the question they had is, why doesn't it add to 100%?
The reason it doesn't add up to 100% is some of them had no trend. Stable was actually stable. The concentration. There are certain percentage of wells where it would go up, down, and we couldn't extract any trend, but I don't want to call it stable. It was just crazy.
Okay. This next question says, thanks for sharing all the good work. Can you talk about the differences between closed system bench scale tests and field data? Once degradation is confirmed, are there different cis DCE or vinyl chloride rates observed in the lab than what we see in the field, and what could be some of the reasons?
In the lab, you have essentially near ideal conditions in a completely mixed reactor. So we're adding our organic substrate, we're buffering the pH, we're making everything absolutely ideal, and so we get great removal rates. In the field, conditions are less ideal. I will argue actually I don't have it here, But in this well, in actually the injection well, even though it was in the field, that was nearly perfect conditions. And we saw fantastic removal rates of things. So I think there are locations in the field where you can approach ideal, but there's certainly, that's the injection well. 10 feet down radiant, it was much, much less than ideal. And so when you average that over, you have some areas that are treated really well, some areas that are not treated not quite as well. Yeah, the average rates are going to be much, much lower.
Okay. Do you find that naturally occurring TOC is typically dominated by high or low carbon compounds?
We've never done any analysis of that. Now, there are some other, in monitored natural attenuation studies, people have shown that natural organic carbon can drive reductive decoordination. But in general, those organic carbon compound, the natural organic carbon is relatively refractory. It does not ferment to hydrogen and acetate, and the bugs we want need hydrogen and acetate. So there may be a couple milligrams per their natural organic carbon. That may be enough to drive some limited degradation, but it's certainly less easily degraded material.
Okay. On the slide where you were talking about TOC moving down gradient, does that data also consider the volume of the fluid injected, like the number of pore volumes that were replaced?
No, we did not have any ability to, let me actually go down to that. This was just data from, I guess it was 47 different projects at different locations. We went to previous monitoring reports, extracted their data, compiled it into a big database. It was very rare that we had any really good understanding of how the distribution worked, how effective the distribution was, and how much physical displacement there might have been.
Okay, there are a couple of questions about nutrient limitations. So can you talk a little bit about that and why ammonia, for instance, would be important for the helicocoides, and if you've seen success adding nutrients?
We have I will not say that. Okay, so number one, I am sure there are a number of locations where you do not need to add nutrients. You do not need to add B12. You do not need to add ammonia, and you can get very, very good removal. I have also seen several of my own sites where, for whatever reason, we didn't. I was cheap or dumb or whatever, and well, we've got really good activity and we've already got good DHC counts, so we didn't add B12 or we did not add ammonia, and got terrible removal. And it just, we got very good conversion in TC to DCE, but we could never get it further. And I can probably count 5 or 6 or 7 different sites I've worked on where, and then in 2020 hindsight, we went, well, was it because we didn't add B12? Was it because we didn't add ammonia? And we went back and we added, honestly, the second time I added 5 times as much as I needed. I added a boatload of B12 and had a lot of ammonia. And I think virtually every one of those sites, well, some were lab studies, a couple were lab studies, there were 2 or 3 different field studies, and DHC took off. We got great conversion, great ethylene production. And so I firmly believe there's a number of sites where you don't need to add it. However, today, we add it at every single site because it doesn't cost that much. And having to go back to your client and tell them, oh yeah, well, we tried to say, we wanted to save a couple bucks, so we didn't do that. So yeah, sorry, now we have to mobilize out in the field and spend a couple $100,000 to re-inject because I was in, well, anyway, we won't go into that. Now in terms of the ammonia issue, if you ask about that, I can refer to you. I can send you a copy of a paper by Frank Loeffler's lab where they actually looked at that, and they have some pretty good data on that. But sorry, I can't recite that data off the top of my head.
Okay. Can you talk too a little bit about how you use molecular biology parameters? One of the questions is, did you look at vinyl chloride reductase in combination with any of those, and what insight did it provide? And then another question that's kind of related to that as well is, what molecular tools do you think would be helpful to show you that there's a stall that's likely to occur?
I didn't show you the data because I don't have enough data to make nice graphs. But in those cases where we saw a stall or again, I'm always hesitant to use the word stall, that persistent higher levels of DCE than we wanted. We had low levels of DCE, 10, 100, maybe even 1,000 cells per, I believe it's cells per mil, usually an order of magnitude roughly lower of vinyl chloride reductase. So we had detectable levels, and we were making some ethene. But when we went back and we adjusted the situation, we raised the pH, what we often see is the DC numbers would jump by at least a log unit, maybe 2 log units. So we had some DCE or some DHC. They were surviving. The indicator, the genes were indicating that we had some low level of activity, but not great. And that's what I tend to see is when we really have these systems cranked up, it's not uncommon to 10 to the fourth or even 10 to the fifth cells per mil of DHC. When we bio-augment, but the conditions aren't right, we'll often see 10 or 50 or 100 cells per mil of DHC, but it sort of just stays there and it bounces up and down, and we got some bugs, but they're not growing. And yeah.
Okay. If you see a decreasing trend in chlorine, is that what you would do, is to plot that to have evidence that you're getting reductive dechlorination? And if you saw a stable trend in those numbers, would that be indicative of a stall?
Yes. I would plot them versus time. If we're seeing decreasing numbers, I would indicate that it's progressing the way we want. You can even use those numbers to project out. If it's stable and total organic chlorine is not going down, then you're sort of at a stall. Now, I will tell you at this site that I'm pointing to right now, we were down gradient of an untreated source zone. So it wasn't exactly back diffusion, it was just simply there was an area up gradient of us that we didn't know was contaminated, so we didn't inject it. And what was happening is this area was acting almost like a biobarrier, where we had contaminants from up gradient being released, migrating down gradient into this zone. They were getting partially degraded, but since we didn't find all the source area, we were continuing to get a bleed in of TCE for, probably almost a decade there. And it wasn't until we went upgrading, we found that other area, treated it, that suddenly things started to take off.
So a good question on this. Did you attempt to use CSIA? If not, do you think that isotopic fractionation could be helpful for you in understanding this?
I know a lot of other people use CSIA a lot more, and they find it very effective. Where we used it is more in M&A cases, where usually with chlorinated solvents, where there's really no doubt this is degrading, it's just not degrading as fast. CSI will not tell you necessarily why it's not degrading, it'll just tell you it's not degrading. So there's certainly a number of cases where CSI, I just personally don't use it that much, so I kind of don't want to comment.
Okay. Did any of the molecular work that you did identify dihalogen
Certainly, we have seen that often at sites, and usually the numbers are not, for whatever reason, we've monitored that, we've seen that in a number of sites. It is certainly possible that that's an alternative vinyl chloride reducer, and I can't comment much more because I'm trying to get my arms around that one also.
Okay. There's one question that was addressed to me. It says, are Dihalococoides McCartyi populations measured in the quantarray chlor? And yes, that is one of the organisms that are on the quantarray chlor test. So when you do that, you'll get that result. Okay, this one is for you, Bob. It says you probably have tested bioaugmentation and pH buffering to help you overcome DHC stalls. Is there something that you find performs best for you?
Yeah, and honestly, our experience now of not wanting to go back to the client, ask for more money is virtually every site we go on, it is very rare we do not bioaugment. If the pH is less than optimal, we will always adjust the pH, and we'll now add B12 and nutrients virtually every time, just because I don't like going back asking for more money.
Yep. Have you seen sites where methylene chloride is one of the chlorinateds in the mix, and what did you find how that affected what was being treated?
We've certainly had methylene chloride sites, and methylene chloride by itself was never a giant problem. Now sites where you have carbon tet or chloroform, chloroform particularly can be inhibitory to some to the bugs that degrade chloroethanes can be inhibited by chloroform, and that certainly can be a challenge. Methylene chloride has not normally been a problem for us, but I honestly don't know that I've worked on more than one site that had significant methylene chloride.
Okay. When you've done pH buffering and made adjustments, do you have something that works best for you when you're doing that?
Yes, but that's the second half of my presentation. So Dora, are we getting towards the end, and should I sort of move on, or?
Yeah, maybe we should go through that. And then if we didn't get to your question, we can do a summary at the end, and that way we can hear the rest of this from Dr. Borden. Does that sound okay with you?
Okay, but it's now 11:59, so I have 1 minute left.
Well, I think if we go a few minutes over, we'll just keep recording if that's okay with you. And then if people have to leave, the recording will be available and they can listen to whatever portion they missed.
Okay. All right, let me. Okay, so how do we bring contaminant into direct contact with oil? I think several issues that have come up before that we've identified as significant issues is, one, underestimated maximum oil retention, stagnation zones, and untreated zones. So first of all, this is we've been doing this for a while, where what we'll do is we'll essentially measure how much oil can absorb the soil, and we'll try to design our injections based on that. And what you're seeing here is a picture. It's a lab column. We have some EOS. We pump it through the column. You can see it turns a little bit white. We pump 3 pore volumes through. We flush it with water, and then we measure the amount retained. And what we've seen is that, not really surprisingly, silts and clays hold more oil than sands. The surfactant type non-ionics tend to have lower absorption than ionics. But the other thing that recently is we've seen is that the zeta potential, and I'll talk about that in a minute, but if you have the oil, the emulsions we make are negatively charged. If the sediments are negatively charged, the oil droplets will be repelled by the sediment, and we can transport them farther before they're captured. And I'll talk about that in a second. So these were early tests. We did most of these in the lab and a little bit in the field, and we measured maximum oil retention from a number of different soils. And the thing you see here is most of these values are anywhere from 0.5% to maybe 1% by weight. And so we sort of developed this, and kind of my rule of thumb was 0.5% to 1%. That was the kind of oil retention that I thought was typical. And in certain aquifers it'll be even lower, but that's not a bad number. Since that time, thanks to Microbial Insights, for any of you who don't know, Microbial Insights will run those oil retention tests. And so they provided us a bunch of data, and we looked at it, and again, I plotted cumulative distribution. And what you see is virtually all the early data we had was less than 1% by weight. But in some of the Microbial Insights data, they have much higher numbers, maybe, of 5, 6, 7% by weight. So you're talking about a lot of oil to treat these areas. And that was really surprising to us. We didn't really understand it. And I still will say I don't fully understand it, but we think we have a hint. At a few sites, what we did is we went out and we measured the zeta potential of the soil and the EOCVO in deionized water and in calcium chloride. And what you see is that in deionized water, you have a very strongly negative zeta potential. In calcium chloride, the zeta potential is a lot less negative. So here, if we were in DI water, the oil droplets have -43, the sediments -20 something. So I don't know, maybe that's a repulsion of 60 millivolts. And in the presence of calcium chloride, the zeta potential is a lot lower. So there's a lot less repulsion between the oil drop and the soil. It's a lot more likely it's going to bump into it and stick. In the same test, when we go back and we measured maximum oil retention, in DI water at these 2 different sites, you can see, well, anywhere from 0.03 to a little bit over 1. Maybe that's a little higher than we judged before, but it's not terrible. But now in the presence of calcium chloride, we're getting a factor of 4 increase or a factor of 3 increase in oil retention. So bottom line, if you have a hard water aquifer where you've got a decent amount of calcium or magnesium, it's quite likely you could have significantly higher oil retention than sort of our rules of thumb were based on. Similarly, if you're adding calcium carbonate or calcium hydroxide or magnesium hydroxide, you're adding hardness to the water, and that needs to be sort of taken into account in that process. Another factor to think about is stagnation zones. This was one of the issues early on. I said early on it didn't get fully treated. Well, this is the picture at the top is what you would think of as a barrier. And we're going to go out and we're going to install wells at A, B, C, D, and E over here. And we're going to inject. If we inject all the wells at the same time, which typically is what the field guys want to do, they want to get it all done and over with. Well, if you're injecting at B and C at the same time, you've got streamlines coming out from C to the left and B to the right. Well, when those streamlines bump into each other in the midpoint, you're going to get a stagnation zone. Oil's never going to get to that point. And instead, since it can't go into that zone, it's going to get pushed up or pushed down. That's why these blobs aren't circles or more ovals, is because the stagnation zone that forms in between. Now, we did some modeling to try to figure out, well, okay, really how important that is. And we looked at two different things. One, simultaneous injection. That's this lower line. And for the amount of oil we're injecting, and it wasn't that much, we're getting a maximum contact efficiency of about 75%. If what we did is we changed the sequence and we injected wells A, C, and E one day, finished that injection, and the next day came back and did B and C, or I'm sorry, B and D. When we're injecting A and C, the stagnation zone would be right here at B. So the first day, we wouldn't treat this area. But the second day, we'd have been injecting right in the middle of the former stagnation zone. And basically got another fact, a 10% increase in contact efficiency. Now, it's not perfect, but it didn't, if you work this out properly, it doesn't increase your time in the field at all. All it does is, yeah, the field guys have to run their hoses a little bit farther. And instead of doing one area the first day and a second area the second, they sort of do half of both areas each day. And so it's a little more work, but realistically, the incremental increase in cost is just tiny. Okay, another factor was limiting treatment. This was in site, one of the earlier sites we did. The conceptual model for the site was that there was a lower, the primary contaminants were in the B zone and the C zone. This is where they wanted to treat. So what they did is they went out here, they injected in the B zone, they injected in the C zone, monitored, and what we saw is in the B zone, we had excellent, I don't have a whole lot of data, but all the data suggests that we were getting excellent removal in the B zone. We were also getting very good removal in the C zone, but there was about a 5-foot gap between the bottom of this well and the top of this well. And well, not surprisingly, didn't get very good removal there. And that's why I keep beating on, the dissolved organic carbon. It might migrate a little bit, but it really does not migrate far at all. You have to bring the oil right to the contaminant if you want to get good removal. And I think this is a sort of perfect example of that. The next part of this presentation is, people asked about how do you adjust pH? How do you determine how much pH buffer to add? We developed a design tool for ESTCP that does that calculation. I'm thinking I should stop now. This is a whole separate presentation I give regularly. I'd be happy to, if anybody wants to learn more about this design tool, I'd be happy to share it to them, but well, I still got a ways to go, and yeah, I think it's time to wrap up. One last thing, I'm going to scroll along here. Don't hope this isn't making your eyes go bad, but the EnviroWiki, if you have, I'm sorry, if you have questions about it, Most of the things I've talked about today are on the EnviroWiki. There's emulsified vegetable oil. This sort of explains the conceptual model. We've got modules, the design tools that I didn't get to talk about is here on the wiki. It's got a pretty good description. If you need more information, I'd be happy. As well as a lot of other, on explosives, on other contaminants, on 1,4-dioxane. Excellent resource. I hope you'll check it out. And thanks so much, but I think I'll stop the presentation part now, and if we've got time for more questions, we'll do it.
That sounds great. Well, thank you very much, Dr. Borden. I think it was really interesting. We do have quite a few questions that are left. We'll get through a couple of them, and then if it's okay with you, Dr. Borden, what I'll do is send you a Word doc with the remaining questions we didn't get to,
Sure thing.
and then maybe we can just send out a Word document to everybody that attended so everybody can hear those answers.
Okay.
Okay. Can you talk about the types of buffering agents that you would recommend?
Well, as people know, we use magnesium hydroxide a lot. I like it because now its downside, it does increase the hardness, so that is an issue. But it's relatively insoluble and it doesn't generate we can inject it since it's got a relatively low solubility. It lasts a long time. Initially, actually, what happens is magnesium hydroxide by itself has a pH of about 9 to 10, which is too higher than we want. But we find that when we inject it very, very quickly, essentially as soon as you produce CO2 or there's any CO2 in the atmosphere, the CO2 precipitates on the surface of magnesium hydroxide, making magnesium carbonate, and the pH is about 7. And it stays there until basically all the magnesium is dissolved away. We've had sites where we can do a one-time injection and we'll maintain a pretty nice neutral pH for 2-3 years. You can use sodium bicarbonate. The challenge with sodium bicarbonate is it's not a very strong base. So, sodium bicarbonate will get you up to a pH of about 6 or 6.2 pretty easily. It is very, very, very difficult to get up above to pH 7 with bicarbonate by itself. You can use things like sodium hydroxide, but I do not like to use sodium hydroxide because essentially the challenge is, you inject sodium hydroxide in your well, the pH won't be 5, it'll be 14. So we basically never use sodium hydroxide. So our preference is magnesium hydroxide, but that's our preference.
Okay, great. Well, I'll do one more question, Dr. Borden, then I'll send these over to you because there's a lot of still good questions that are left. How often do you recommend that people apply or inject the oil or the long chain fatty acids?
Typical rule of thumb is 3 to 5 years. There are certainly, we've seen some sites, real high velocity aquifers that I'm going to refer to a perchlorate site where astronomically high groundwater velocity, I think 50 or 100 milligrams per liter per chlorate and nitrate. There, they have to re-inject every 6 months, just because the water flows so quickly and it's got such a high electron acceptor load on it. We've got other sites where people inject the source area and relatively low groundwater velocities. It's nice and anaerobic and cook along fine 6 years later, and you don't need to do anything. So it's really a range. It depends upon how fast the groundwater velocity is and what the background electron acceptor concentration is. If you've got a lot of nitrate, a lot of perchlorate, a lot of sulfate, that can certainly burn up the electron donor much more quickly, and you may have to re-inject more often.
All right. Well, thank you so much, Dr. Borden. That was an amazing webinar as always from you. I know there have been a lot of questions about getting a copy of the slides. You can email info@microbe.com and we'll be glad to send you a PDF of the slides. And if you have additional questions, you can also email them to us or to Dr. Borden. And I have about 10 questions that are remaining from the webinar that I'm going to send over to Dr. Borden and let him write some responses, and we'll send that out to you, to all the registrants, so that you can see those answers as well. But thank you everyone for your attendance today. It was a great webinar. Thank you, Dr. Borden, for your time. I always love hearing you speak, and I really appreciate all that you do for us.
Thanks so much, Dora.
All right, you guys all have a
Thanks
wonderful day. Thank
everyone.
you.
Okay, bye-bye.
Bye-bye.